guys don't have to take all of their dirty, muddy, whatever out. And they get to stay. But you don't. Oh. Then we'll have lunch. And then in the afternoon session, everything is going to be innate. Okay? Please turn off or mute your cell phones. And I can't think of anything else to say, except today let's see. I got to read you what your presentation is.
Feel free.
Proper fluid selection. So, okay, we're talking drilling mud here, not whiskey. So anyway, Jose Serna and David?
Yes.
David Horton here to present from MI SWACO?
SWACO, that's it.
SWACO?
Yes, sir.
Gotta make sure I say it right. So, pay attention. Thank you.
Thank you, Marvin.
Stay awake. Stay awake.
And good morning again to everyone. Thank you for coming. Thank you for being here on a Saturday, no less. As Marvin said, we're going to go over proper fluid selection today. My name is David Horton with MI SWACO with the technology team in Houston headquarters. Jose Serna is my partner today. We both have nearly a decade of experience with MI SWACO and more than that in the mud business. So we hope to share some of that knowledge with you today and continue the education as National Groundwater or New Mexico Groundwater has asked us to do today. Proper fluid selection is the title of our presentation, so we're going to center the lesson on that. And what I'd like to do before we leave is make sure anyone that has questions on fluids and muds can get those answered before we leave. So we have a 2-hour session. We're going to take about the first hour for lecture and some review of knowledge and skills about fluid selection and why we do the things we do with mud. And then we'll do some hands-on. Part of the portion today was requested to be a hands-on experience for everyone. So what we have here are some mud testing apparatus, and Jose is going to walk us through those step by step. We have enough material and capacity here to do at least one full example of those tests, and then we have some fresh water that everyone can do safely. If they wish to, get your hands on it, come up here, and we'll walk you through step-by-step experience with the testing equipment, and then answer any questions you have to make sure you're doing it right, make sure you understand why we do it, and what it means for your mud and your operation. As Marvin mentioned, we've got about a 2-hour session here until you switch to ballroom A. Bathrooms are out the door down this hallway, and then if there's an emergency for any reason, we'll take the exit here and walk out the south side exit, just so everyone knows what we're doing today. Cell phones, please, if you get a call you have to take, please do so outside. And also, please be interactive with us today. We don't want crickets in the audience in silence. We'd like to hear some questions and make sure we have everyone's attention throughout, and we get those questions answered before we leave. So let me go ahead and dive in today with proper fluid selection. The first thing we're going to discuss is the importance of a drilling fluid, why we use a drilling fluid. We don't always have to, for example. What that drilling fluid does for us. And then the next step of that is when is it doing it correctly? Or what is a good mud? We're going to come to that later. But it's a key question, and what we look at for proper fluid selection is what is a good mud? What's a bad mud? And what's the wrong mud for your job? These things we can show you with the testing. We can show you with some of these slides, and hopefully everyone can have a better understanding of how to apply fluids for their operation after this. We'll have a general fluids discussion around what the fluid can do when it comes to different soils we interact with. Reactive clay is going to be much different than depleted sand, for example. And we want to treat the fluid differently when we're in a production zone versus when we first spud the well. So these things we can graduate as we go through the discussion today. Again, we'll focus where your attention is needed. And again, hands-on session at the end. So we look forward to doing that. And we will take questions at the end. We'll spend at least 10 minutes to 15 on a recap session and any points that we don't get to in the first go-around. But let me dive into some of the meat of the discussion today, and we'll go from there. So proper fluid selection is important to everyone's operation. Some of the key things that it will do for you is reduce your risk. It will help your efficiency. It will help the production of the well in the long run. And with those two things accomplished, you're going to improve your efficiency of your operation and therefore save money. And that's what we're all after at the end of the day. If you make money, we make money. The customer is happy. So we're all in this together. The fluid should work for you. It's one of your best tools when you're drilling a well, and we just want to make sure it's done properly. So why is a drilling fluid needed? Does anyone in here just drill with water? Only water? Raise your hand if it's you. Okay, we have one. Anyone else? No, that's good, because we have some fluid experts in here I can see then. For anyone that drills with water, the question we have for water used as a drilling fluid is, when can we use just water to drill? And the answer is, every time we can. Absolutely. Until we can't. And that's the big question that we have to ask ourselves when we choose our fluid. Are we going to try this with water? Can we do it? Do we have enough water supply? Is the well stable enough to take water and not be unstable? And will it not cause damage to the production zone in the end? So with those things addressed, we move on to selecting our mud, a true mud that has both clean and dirty solids in it, that has engineered additives for certain responses and performance in our fluid. And that's what we'll get into today, why we do things for different soils. What we should consider when we look at soil conditions. Again, we'll get to that with specifics, and some of this testing will really illustrate how that mud is doing what we ask it to do. So what is a drilling fluid for? Okay, we need to establish the basics. We need to know why we're doing this so that we can know when it's working and when it's not. One of the primary things we look for is when it's cleaning the hole. When it's removing those cuttings as we make a new hole, as we excavate that earth, we want it to be unloaded from the hole. We want to remove it efficiently, and we want it out of there so it's not re-drilled. If we re-drill it, then we're drilling slower. We're going to wear out our tools sooner. It's going to slow down the entire operation, and it could lead to other headaches in the future. So we want to avoid that by doing proper hole cleaning. If we're cleaning the hole effectively, then we'll also stabilize it. Stabilizing the hole means not causing disruptions that we see later. For example, a tight hole when we trip out, or excess torque when we're drilling ahead, those sorts of things. We want to suspend cuttings during static periods. So every time we make a connection and we shut down our pumps, we don't want those cuttings to drop to the bottom. When we do that, it could potentially pack around the bit and cause a stuck pipe situation, or a pressure surge, which is also potentially hazardous to the hole. And then in the end, we want to prevent formation damage. We want to make sure that solids are removed that are unwanted so they don't go into those porous spaces we need later for water to flow through. So hole cleaning can prevent several problems from happening. We don't want to have slow penetration rates. Again, we do that by getting those cuttings away from the bit. We don't want to have excess torque and drag. So we don't want to have a hole full of dirty cuttings that are in the way of our pipe and our string. We don't want to have stuck pipe. And of course, we don't want to lose circulation while drilling. That's potentially one of the longest delays we can have, is if we lose circulation unexpectedly. Then we can have all sorts of other headaches on our hands. And I've just realized I'm looking at a slide ahead of you on this presentation, so forgive me. But let me go back, because there's something I wanted to do before we end today, and that is, what would you like to learn? So I brought a notepad here because we don't have a whiteboard. I'd like to display it for everyone to see, to know that you're being attended to. But if there are any questions that people have, please raise your hand now and let me know. I'd like to know any questions. I'll write them down, and at the end, when we recap and review what we've learned today, I want to make sure that we've covered those questions. So do I have any questions? Proper fluid selection? You're good? Marvin's good. Okay. The team is good? No questions. Okay, I'll ask some questions as we go then about that. And it may be on your mind as well. But if we cover those, hopefully we're all good, Marvin. I'm trusting you here. Okay, so proper fluid selection at the end of the day will help us save money. That's right. That's right. Thank you. So let's get to some mud rules. These are a simple, straight to the point set of rules. There are 6 of them that will help you remember the rules of mud. Now, mud is designed to keep you out of trouble, not get you out of trouble. There's a big difference there. Once we're in trouble, it's back to the drawing board. We have to start over and look at how we got in that mess and how we're going to get out. The fluid may not be the answer. Where the fluid can help you is how to prevent that trouble from happening. If we can prevent the trouble from happening now, at the end of the day, we're going to have a more efficient operation. So there's no such thing. Mud rule number 2 is a universal soil, and therefore we shouldn't have a universal mud. If you ask me now, what's the best mud? I don't know. The answer is, what kind of soil are you in? How fast do you pump? What kind of mud cleaning equipment do you have? And what problems have you encountered in the past? So we know what challenges to address. Once we discover those things, we can tailor the fluid for that particular well, and we can make it work for you. But out of the gate, we don't know what we're going to encounter. Therefore, it's very hard to plan the best fluid for you. So if there's no questions in the audience, I'll ask the questions today about what we should think of before we start things, or why we would do something with mud versus something else, or not do it at all. Adding the wrong amount of mud additives can be potentially more hazardous than adding none at all. So similar to maybe a baking experience that someone has had. I like to use my mud engineering as some baking comparisons, but if you're trying to bake a cake and you add too much oil, you're going to have a cake that doesn't stay together. If you have too much water and not enough flour, you're going to have things that don't work. Or too much flour and not enough water, on the other hand, your cake's going to look more like a brick. It'll be hard to eat. I had sort of a similar situation with my gingerbread cookies this year. But first time, so maybe next time I'll get it better. The point is, when we misuse mud additives, using them when we don't need it, or using the wrong thing for the job, it can potentially cause you more harm than good. And that's really throwing money away. We don't want to make that mistake. So preventing mud problems is much cheaper than fighting them. That's mud rule number 4. We want to prevent those problems. We don't want to throw away chemicals down the hole. We don't want to use them excessively. But properly choosing those will keep you out of trouble. Now, the performance of the drilling fluid is directly related to the amount of solids, unwanted solids in that fluid. This goes back to hole cleaning, but the number one thing we can do to a mud is keep it clean. That's the most important thing we can do to maintain our mud. We keep it clean by adding fresh water or using solids control equipment, or both. But with dirty mud, we're going to have all kinds of problems, and unfortunately, the way to help that is very costly. We get into high dilution rates. We start adding too much fresh water, and all of a sudden, we might as well start over. It'd be cheaper to displace the whole system and start fresh. So we don't want to get into those snowball effect situations of problems. More complex problems may require more complex muds. That's the last final mud rule here. So depending on the challenges you have, as you know, mud companies come with a long list of additives and recommendations we can give. So the more complex your problems, it may be a more complex answer. But that's why we have these tools in testing to help us identify that. And you have people like Jose and myself to go to and ask when you encounter these things. Now, I hope everyone's been paying attention. It's time for the test. Jose, did you bring that? This will be graded, and at the end, no credits for any failures. Okay. Now that's my joke. I had to build that in to keep your attention up. But, and I'm glad I didn't misread the slide. But what we'll do instead is just talk about mud testing, okay? So we go back to the question, is it good mud or bad mud? Tests need to be performed to answer that question. We can't just tell. And trust me, I've seen it too many times where people with a lot of experience can make an unwitting mistake when they think the mud is good by looking at it, but it needs more than the eyeball test. It needs test equipment. It needs more than one test equipment, most likely. So we don't know if it's good or bad until we test it. Now, tests need to be performed correctly, and that's what Jose is going to go over. A simple miscalculation of a stopwatch or not knowing where the mud fill line is on a mud cup can cost you misidentifying a problem and having a headache you don't want to have to deal with. So there are 5 basic tests that we're going to go over today. There's many more. I list 2 here as additional tests that are common in the mud business. Truth is, there's probably more than 10. But not that we need to really concern ourselves with, and not that we are going to demonstrate today. So we're going to stick to the 5 basics of classic water-based mud tests done properly, and use those to identify and maintain our proper drilling fluid. Those 5 tests are marsh funnel viscosity, and I'll grab that so you all see what I'm talking about. This is the marsh funnel. Okay, this is your funnel cup. This is the mud cup. And the 2 go together when you perform the test. You'll also need a stopwatch, but I'm going to assume most of us have a stopwatch available whenever we're at a drilling operation. So these are the 2 main components of this test. Jose's going to show this to you later today, but that's what I'm talking about. Sand content is here. We have the glass tube that's used and the mesh screen that's used to perform that test. Sorry, I skipped mud weight. Mud weight or fluid density is here. We have the mud balance that will show how to weigh the mud and identify what the density of that mud is. We'll also talk about what a good mud weight is and when too much is too much. We'll look at pH testing, why we test pH, when we test pH. It's important to identify the water source pH before we even add the first mud chemical. And then we'll look at filtrate control. It's probably among these tests the most complex, and so it will take the most time to demonstrate, but we would like to walk through with anyone curious enough the actual steps hands-on with this at the end of the session today. So any curiosity seekers will find the test available to them today. So viscosity is, we see that in maybe motor oil in common things. But when we talk about viscosity in mud, what we're referring to is how thick the mud is. We all know that mud can get too thick. We all know it can be too thin. But we don't know how thin or how thick it is by just looking. We don't know by just seeing it come out of the flow line or return from the hole. We don't know until we measure it, and that's why we use the funnel viscosity. Mud that's too thin may destabilize the hole. It gives a different flow regime, and it gives potentially too much fresh water to the hole, so we want to avoid that. And we want to have mud that's not too thick on the other side of that. Too thick causes excess pressure, causes potential hole problems with lost circulation, and puts excess strain on all of your equipment, pumps, liners, solids control, even the bit, and wall cake. Exactly, thank you. And we'll show you an actual filter cake on the API filter test later that will be indicative of what the wall cake is, so you can see what we're talking about. But that's one of the most important factors that mud can do. So the test cup is here. Just as a baseline, everyone should keep in mind that water has a viscosity of 26 seconds per quart. The quart line is this fill line inside our mud cup, and we'll show that to everyone during the hands-on portion. But 26 seconds per quart is fresh water. So anytime we're not confident that our equipment is in check, we put fresh water through this funnel cup and make sure that it's 26 seconds per quart. Now, how would it not be correct? There's an orifice here that is a special size to give us the 26 seconds per quart. This can get washed out, it can get reamed out, or it can just fall out. You can come up here and look, but it's metal, and it's of a certain size for that exact reason. So the other thing that could happen is you've got too much residue of old mud inside here, and it's not giving you a full volume of mud at your fill line here. So you're not testing a full amount of mud. So if you're not running the test correctly, final thing that could happen is there's a mesh on one side, there's an empty entrance on this other side. We always want to pour the mud over the mesh, because if any solid or particle goes in here that potentially plugs our hole down here, then we're not going to get an accurate flow of that fluid, and therefore not an accurate viscosity reading. So we want to make sure our equipment is clean, in good shape, and ready to use before we use it, and then we can conduct the test properly and get a good reading. The next thing we have is drilling fluid density, or mud weight, MW. You see that a lot on reports. Density is essentially how dirty the mud is. So dirty mud, we always call drilling fluid mud because it's dirty, and we know that. It doesn't take long to get it full of solids from the soil that we're drilling. But we want to minimize that as best we can. And one of the first checks we can look to see if we're doing that effectively or not is the mud density. So fresh water has a density of 8.3. Common gallon of milk has a density of about 10 pounds per gallon. So those solids inside milk, for example, cause a lot heavier fluid, a lot higher density. And we see the same thing in mud. So when we start with fresh water, we know it's 8.3. As soon as we add bentonite, it's kicked up to 8.8, 9.2, depending on how much bentonite we put in. And then when we add the drilled solids, that's when the mud weight really goes up. So we try to limit that 9.3, 9.4, depending on how deep or the type of soil we're drilling. But we want to run this constantly, potentially every hour or so while we're drilling, to make sure we're not letting the mud get too thick, too dense, and too heavy, which is going to cause all kinds of unwanted problems to our hole. So we have it here. It's a balance. It's calibrated by adding or taking away metal or solid material to this end. There's simply a screw that opens up, and we can take or add a dense material to this end. It can be sand or metal. And we put our mud in the other end, and then we set it on our balance to measure the density. We always want to check this with fresh water before we start any job and make sure that it's calibrated. If not, we change things here. A sand content is just that, how much sand is in the mud. Now, sand is not just necessarily play sand. It's defined by micron size. So a certain mesh of material is considered sand. Above that is other material, cobble, gravel, what have you. And below that can be colloidal. But what we check in this test is a visual test with a clear glass tube, how much sand is in our mud. Now, sand can be a big problem. It tears up pumps, liners, and seals. It wears out everything from the bit nozzles to your hoses. So the more sand we have in our system, the more problems we'll have with equipment. Potentially more problems you'll have with the hole as well, because that sand is going to have an SG of around 2.6. That means that our density is going to increase, and that once our fluid is too dense, we'll have those problems. So the sand content will identify sand as the problem. The density will indicate before that you have a solids problem, but we don't know what sort of solids we're dealing with until we look at the sand content test. pH and alkalinity. We always run mud on the pH scale on the alkaline side, meaning above 7, which is neutral. The ideal range is between, and this is a rough a rough estimate, but generally between 8.5 and 10.5, depending on what sort of mud and what sort of water source we have. It's very tolerant. The additives are typically of the pH range. What may not be tolerant is the soil we're in, the clay that we have, which tend to react more readily to the pH changes. But also it can indicate if we've got something unexpected in our fluid, or potentially a fresh water flow, or volume coming from an unexpected source, right? Or before we expected it. So the pH we want to actually check before we add any mud additives at all. And the reason we do that is to make sure that we start with something that's near fresh. If it's not, then we know that it's hard water, perhaps, or fresh, or maybe even slightly acidic. But at any rate, we want to adjust that before we add our mud additives with soda ash, sodium carbonate. What that does is two things. It raises the pH, which is a friendly environment for our mud additives, and it also treats out calcium hardness, which is a performance inhibitor to mud additives. So if we don't do that, then at the end of the day, we'll end up using more additives to accomplish the same mud. But if we start with our water and treat it for pH first, we'll have the right environment for a good, proper mud to live. That also will reduce the amount of bacteria that could potentially thrive in our fluid, similar to the reason why we have things like sodium bicarbonate in ketchup bottles. Things that shelf stabilize require pH adjustments to do that, or we might add a little vinegar on the other side to get it shelf stable. So pH is critical. It can be measured in two ways. There's the common test strip, which is a simple paper strip that has a legend, and we'll simply dip that strip in our mud or the water and see what color it brings. Or there's the meter, and we don't have one here today, unfortunately, but they come in many shapes and sizes, and all are a similar digital readout. So they're a very straightforward way to dip this indicator in the fluid and have a digital readout of what the pH is. From there, we need to adjust if necessary, or not continue and add your additives to the mud as what was planned. Sorry. So the strips you can see on the left side of the screen there, and the meter's on the right. Again, the meter is not something we have a specific name brand or model design preference, but something that just measures anywhere in the common pH range of 0 to 14. Now the API filter press is I believe the last piece of equipment we're going to review today. And this is one of the most telling of the tests that we can do, because it gives us two things. It gives us filtrate, and it also gives us a filter cake. So both of those will indicate something about the mud and something that we need to treat. A low filtrate volume is generally what we try to achieve, and we do that primarily with bentonite. But beyond bentonite, there are many additives that we can add, commonly referred to as polymer, but these can be a cellulose, and those come in many shapes and sizes, many forms. Common term you'll hear for those is PAX, polyanionic cellulose. There's also HEC, or hydroxyethyl cellulose, or sodium methyl cellulose. There are many types of cellulose that are all serving the same purpose, and that is just like our cotton shirts are woven together today, they bind together the filter cake. They're like a thread that ties particles together and hold it tight. And so when they tighten the filter cake, we have less water pass through. And that's good for the whole, because water will destabilize the whole. We don't want to give it excess fluid in the shape of mud or water. So a good filter cake will prevent a lot of problems and potentially save the day. Filtrate volume in general, we say a 15 is a good rule of thumb to know as a high or low mark to keep in mind when it comes to measuring filtrate. Typical bentonites at a typical concentration will get you probably around a 15 to 18 But if you're up in the 20s, you probably are not concerned with filtrate, or you should be, because that's when we'd say it's high. High filtrate is something that we can definitely treat, or it may come into effect after we've treated, which is another situation, which is where we have dirty drill solids in there. They're disrupting the filter cake that we put down and are spending money to build, but we're hurting ourselves by having those unwanted solids in there, and it causes the filter cake to become fluffy. Breaks apart those particles a bit by same way salt would, we salt the roads before it snow, so it prevents the ice crystals from forming, from grabbing hold of each other to form a crystal. Drill solids will do the same thing to a filter cake, and they'll disrupt it. They'll cause little spaces, and I'm talking microscopic, but small spaces where fluid flows through, and we can measure it in the filtrate that we receive in our tube. So that's when we see filtrate rates of upwards of 15, upwards of 20 perhaps. Sometimes it goes into what we call no control, where it's just a straight stream of fluid. It almost looks like the funnel viscosity test of just a straight stream of fluid. So it can get bad. A tight filter cake is something that's below 15. But if we're really trying to achieve a tight filter cake, we would probably want to keep that more closely to 10 or less, which can be achieved. We'll probably have several ways of doing that. It won't be a straightforward approach. Bentonite surely won't do it no matter how much you add. It will require some packs, and it may require other polymers to help it. So we'll need a multiple approach. As I said before, the more complex the problem, the more complex the approach is most likely the situation. In clays, a filter cake is an important factor to minimize how much water we're introducing to the clay. If we're leaching out water to a clay and it's reacting, it can swell, it can dissolve, which incorporates into our mud. Our density goes up, our viscosity goes up, everything gets thick and we don't know why. If it's a sand, we can simply wash it out. We've all seen waves crash on the beach and seen how easily water disrupts sand. So that same thing can happen in the wellbore. We want to prevent that. So in both cases, we want a tight filter cake and a low filtrate to achieve that. So the API filter press, API is American Petroleum Institute. It's a very specific test with specific sizes, and the PSI, the pressure we put on the cell is 100 differential pressure from top to bottom, which simulates a static wellbore with a fluid column, potential hydrostatic head of 100 PSI differential pushing out into your wellbore. So it's not the number one or the answer to everything, but it does give you a very good indication as to what your mud's doing in the hole. Now the filter cake. I heard someone comment on filter cake. Very good call. Filter cake is something that we eyeball test. We look at it. We also have a measuring device for that. It's a small ruler and measured in 30 seconds of an inch. But that filter cake has a very distinctive look when it's what we call fluffy or too thick. That's on the right side, of course. And then a healthy, thin filter cake is on the left side. Thin is roughly 2 30-seconds of an inch or less. More than 2 30-seconds of an inch is when we get into what's happening with my mud and why is it giving me a thick filter cake. So this is a visual demonstration of exactly what your wellbore is looking like. It's not a dynamic situation where I understand the wellbore is dynamic with the fluid passing over it, so the filter cake is constantly being eroded by that fluid passing. But this is showing a very visual demonstration of, in static periods, what's happening. Sort of like what's the minimum damage that we're doing here. Because when we're drilling and we've got the pump pressure coming out of our bit, and we're putting that pressure at the bottom of the hole, that cake is deposited immediately at that point, and that's when the majority of the invasion will happen. So we want the filter cake to be thin. We want it to be pliable. We want it to be slick to the touch. It shouldn't be gritty. It shouldn't be dry. It shouldn't crack. If I put it on the desk and wait for 10 minutes, it should not show cracks. Similar to clay you might see on the surface of land, where in the summer things get dry and you see cracks and clay. The filter cake will look the same way if you have an unhealthy clay in there that's perhaps dehydrated. So it will tell you a lot of things. The best filter cake, if we are treating with multiple additives beyond bentonite, for example, a pack, and we have a filtrate volume of less than, say, 15, we'll be able to peel off the filter paper. Same way you peel a sticker off the back of a sticker page. It will peel, that filter cake will peel right off. And that's what we want at the end of the day. When we're done drilling this well, we want this water to come in and just peel away that filter cake, remove it from the bore, and allow all permeability to return. If we don't accomplish that, then we have unwanted effects of the mud. Now, this is a good visual. I've tried to explain this in many words already, but this maybe help what I'm trying to accomplish by showing you where your drill pipe is in the hole and how those drill cuttings, and these are large here in depiction, but in reality they're much smaller, but how those tiny particles can enter into the native soil, the native formation. And you have to consider that if your filtrate volume is high, then you're just allowing more and more of that solids invasion to happen to the formation. So if we're doing that unwantingly or unknowingly, we'll have an unwanted effect by the end of the day. So to minimize that effect of filtrate invasion, we add our packs, we add our polymers to reduce filtrate. And we make sure we maintain that with our filter press. What you'll see with a mud that's not mixed properly, let me repeat that question, sorry, because we're on film today, to make sure everyone understands. So if a mud is not mixed properly, will we see it on the filter paper? The answer is of course, you will. And it will probably be in the form of fish eyes, what we call fish eyes, tiny dots of particle, either unmixed bentonite or unmixed polymer that are still in solid particle form. And there'll be little bumps on the filter cake. The filter cake should be smooth, and like I said, if you rub a finger on it, it should be slick to the touch, like a lubricious fluid. It should have some slickness to it, and it should be smooth. If you have any bumps in there, it's either unwanted solids or unmixed or improperly mixed drilling additive. Does that answer your question? Okay. Any other questions on filter cake, filtrate, or the test itself? No? Okay. What we're going to do is take a 10-minute health break, let everybody get refreshed on coffee, bathrooms, etc., and we'll come back in about 10 minutes and do a hands-on session. We'll demonstrate all of the tests that I reviewed today, and then at the end of that, everyone that wants to will have the opportunity to come up and actually physically handle the equipment and ask us questions on how to use it. So let's break. Let's go. Yeah.
All right, good morning, everybody. Once again, thank you for coming on this Saturday. Appreciate everybody coming. Remember, first things first, safety. Always be safe. I'm going to start off with some mystery fluids over here. I'm going to let these hydrate before we go into the first test. And then once they hydrate, we'll pass them around so you guys can see. And then we'll go into details what they are. talk about it in a little bit. We'll get back to it. But like Dave was saying earlier, it's like a cooking recipe. So whenever you start off with your mud, I know we're all on time and trying to put it in there and get it going. But it's really important to put it in the proper way because that could help you out a lot. And the first test I want to start off with is the pH. I mean, the source where you get your water is very important. Because if it's hard water, you're going to have, like David said, mix more mud, have a hard time mixing the polymers. So you grab one of these strips or the pH meter, and the first thing you do is just insert it. Simple as putting it in water, shaking it, and then looking at the legend. Oh, did it backwards. Sorry about that, guys. And then you compare. As you can see, this is pretty hard water. You have it here at an 8. You want to have between an 8.5 and a 10.5. So once you get that going, and a little bit of soda ash, the very first step of the cooking. And after that, we go with our bentonites, and then our packs, and then our polymers. Once we get the mud going and we start drilling, one of the most common tests you want to do is the Marshall-Vista test. What you do is you get a sample from the flow line. We don't have very much fluid right now, so we'll just do it with the water you get from the flow line, from the tank. This isn't going to tell you exactly what's wrong with your fluid. It's just going to give you a trend. So, I mean, if you see the fluid start decreasing, you might hit water. If you see it increasing, you get more solids in there. So this is a very good test. Can you help me, Mr. David? So it's good to do it with 2 people, but if you only have one, go ahead. Oh, yeah, hold this. Let me do this real quick. So like you said, we have this screen you want to put it over. That will take all the primary solids out. You don't go this way. And it's important to make sure it's clean, calibrated. Because if it's dirty or you have someone with the wire cleaning the orifice that's designed to make it 26 for the calibration, that could throw your reading off. And like everything else, as a mud engineer, if you call us and you don't give us the right information, we're not going to give the right information back, and then we're all in trouble. So it's very important just to make sure your stuff's taken care of and calibrate often. So what we do is get a timer. A lot of people use their cell phone. I don't know if you have a stopwatch, but always, it's on the phone. Put the timer, all right, put it over the screen, and then just, if you don't mind pressing start, and then you just let it flow. It's good to do it 2 people because it can get hard, it can get heavy. Once you, like you said, the mud varies. We want it to be between a 8.7 and 9.3, but once you get inserted in the hole, you're going to have solids in there, so it's be a lot heavier. So it's a good test to have. It helps us out. If we call and you need help, you can just tell us what the viscosity is. I know for many types of drilling, it's different viscosity recommended, but that's another talk for another day. The next test we go to would be our mud density. This is going to tell us what solids we have, how much solids we have in the hole. Like I said, if it's too heavy, that's where you have the issues. You want to be re-drilling what you already drilled. So it's just going to keep packing off, making it heavier. This test, we put the fluid to the top. There's just water, so it should be around an 8.3. Put it on the scale. Scoot it over until it levels out. A3 is water, as you can see. So, do we have any questions so far? I know I'm going a little fast. Has anyone run these before? Nobody? It always weighs the same. Fresh water. And that's a good question, because if you're having issues with the water, the easiest thing to do is get a new source of water, fresh source, right? Anything, that's going to prevent a lot of the problems with the pH. Next, we can go to our sand content test. This is an important test because we all know sand's very abrasive. It could do a lot of damage to your tools. This is the cheapest part of the project is the mud, and this could determine and affect all the expensive stuff, the tools, the piping, the pumps. So with this test, we fill it up to the line where it says mud, and then with the drilling fluid, and then the rest we add water. We shake it up, get it mixed up. We put it through this cylinder, it has a 200 mesh screen in there. Put it over. Once you get it all through it, normally have somewhere to set this. Put this on there, flip it upside down, put it back on the clear gas, and then with water, we put it over it. Once it all settles, it should tell you the percentage of fluid you have in your, of sand you have in your system. Typically, API, I would recommend about a 4%. I mean, I've been to jobs where if it's not up to spec, they make it, them dump and dilute and start over. So it's very important to just keep track of your sand. Next, we'll go into our, any questions so far? Don't worry, we'll have time after this. You guys come check it out, mess with it, go over it. It'll make more sense then. Someone say, psst, nope. Okay. Next, we'll go to our API press. So we put a Wattman paper on this, and what this simulates is the fluid we're going to lose to the formation while we're drilling and adding pressure to it. You normally want to put about fluid in there about 1/2 inch to the top. Give me 1 second. Let's do the one with the pad. It's not good. I closed it. That's important. Thank you, thank you. That's what it took for you guys to talk, huh? Wait till we get to the polymers. I think this was going on with it, David. Going down to my last one. Yeah, I got another one. That's what I was doing last time. Sorry about that, guys. Where's my other hand? Put it over there. Let me check it out. Where's my other hand? This is the issues it was giving me. So everything's sealed on this one, right? It opens. You're supposed to leave open. Yeah, that's closed. Mm-hmm. There we go. So on this test, we add 100 PSI, and then we time it for 30 minutes. This test is going to help us with our filter cake. We'll be able to see the conditions of what it's doing down the hole, and also how much fluid we're losing to the hole. Here's an illustration of what's going on down there with sand. if you're going through a sandy formation. So when you drill with just water, like David said, when the waves hit you and you're standing on it, what happens? It just washes out under you. It's going to do the same thing when you're drilling with just pure water and you hit sand. You're going to have that water go through the formation. Here we have a sand with bentonite, just a high-yield bentonite. And once we add this, it'll create a filter cake, but you'll notice the difference between that and the one with pack. As you can see here, the difference it does. The water is pretty much saturated through the sand. With the bentonite, you're going to lose some fluid to it. And with time, you'll notice it's going to just probably go half an inch lower than that. But that would be it. And then with the pack, you're going to have that tighter effect that it does, which I have another demonstration show right now. So this is an MI Swaco pack. What it does is it's going to tie up all the loose water, like the conch shirt that we were talking about earlier. You'll see a representation here of what it does. You notice you start losing the fluid, and it turns into like a plastic-like material. Here, you can pass that around. This is what it's doing down the hole, as you can see. It's giving it that extra protection to protect the fluid from going out of the well and anything coming into the well. You pass that on, shake it up. And then we'll let this sit for a little bit longer, and then we'll take it out so you can check out the fluid loss. Let me see anything, any other test you might. Oh yeah, another thing we do is identify contaminants. So if you're hitting cement or something like that, your pH is going to go up, making the cement fluffier. You're going to have a thicker filter cake with the contaminant. Calcium is going to be harder to mix your mud. You're going to have a lot of separation. Clays, yeah. Let's pass these on. What was that? Chlorides, yep. That's another one. We could identify all those with the tests we do. Oh yeah, it'll increase your filtrate so you have more fluid loss. Yeah, I was actually. I'll show you after this. I have another class from 2 to 4 at Sandia. 12 to 4. Let's see. Hey, we're all in the same fluids. And here, I'll pass these around. So what we have here is when you have drilling fluids and you go into a clay formation, a reactive soil. When you drill with water, it's going to let the clay hydrate and it's going to swell up on you. You don't want that to happen. That could just cause your hole. You get those bit ballings, collapse on you. I mean, it'll get tight on you, get the pipe stuck down there. So there's 2 types of polymers we have in there. One's what do we like clay guard? An inhibitor. You have an inhibitor that's going to deteriorate the clay. It's not going to let it hydrate. It's going to just fall apart, make it come up and get out with your shakers and such. And the other one is an encapsulator. What that's going to do, it's going to give you that eminent effect around your cutting. So it's going to put a thin layer on the outside and not let the inside get wet at all. It's going to just keep it dry. That'll take it out as well. Depending on, I mean, if you have sticky clay, I'd go with the inhibitor, but if you have some swelling clay, you definitely want to do an encapsulator. I mean, any questions so far? Yeah, can anyone guess which one's which? Here, I'll let it go around for a minute. We'll come back to that question. And another important thing is you want to get these cuttings out of the well, right? You don't want them to keep going down and re-drilling. You don't want to have stuck pipe, more drag. So here's an example of a cutting down hole. It's this golf ball. I'll also teach a golf lessons tomorrow if anyone's interested. But as you can see here, eventually all fluids, all cuttings are going to go down. I mean, it's gravity. The thing is, we're trying to make them not go down as fast. So in the middle, as you can see the difference. And that's what we want. We don't want these cuttings. I mean, if you're switching pipe, calling it a day, going home for the night, you don't want all those cuttings settling back down to the bottom. That's how you get all your issues. So that's a demonstration of what we're trying to do, how we're trying to help. And, I mean, you could see the difference. I'll pass this around, too, so you guys could. There you go. Don't worry, I got the middle, too. You got them? There you go. You guys can check these out. Let me see. Okay. I'll let them pass around so they can check it out for a minute. HUD bore? You mean max bore? Max bores are one stack system. So it's a high yield bentonite. Then we have extra additives on there. We have an extender. We have a little bit of pack, right? So, what's the shelf life on it? 4 years. You guys still have the max bore? Hey. Let's put context to the story. You bought it 7 years ago and yeah. No. Yeah, that's expired. Hey. Yeah, no, it's got a time shelf, and it doesn't help when you buy them at auctions. You don't know the conditions, the weather, you know. Is it pretty hard, like a rock? No. I'll bring some more Max Bores. You guys can try it out. Some good stuff. It's old. Yeah, I'm just gonna. I was gonna ask. There's no way of saving the cartridge on once I release it. Pretty much done. Yep. Oh, I should. Okay. I was gonna do it early so they could just see it because it's 9:30. No, I'll give it a couple minutes while they pass it around. And so the last test, we have the API press. So I'm gonna give it a couple more minutes, and once it's done, we'll be able to pass the filtrate around. You want a clear filtrate. As you can see, we have that at a 3. So that's a real good filtrate, but like I said, it's in a perfect world right now. And you can see it drips out slowly, and then we'll take out the Wattman paper. You can see the filter cake get created down the hole. So we'll pass that out here in a few. Does anyone have any questions right now? What do you mean, like where should you add? From where? Then the flow line. Yeah, into the tank. Yeah, do you have, what kind of system do you have? Do you have like a above ground tank or with air pits? Yeah, just introduce it as it's coming out so you have time to, but make sure if you check, if you have pH, check the pH and that'll help out. So the air pits, you seen them, right? Yeah, that's right. So you just add it where you add your mud. No. No. He'll address that in a minute. What do you think it's doing that on the? Yeah. What do you think is wrong with it? That's what it did last time. We ran them yesterday. That was my fear, but we played it cool, right? About 9:30 should recap. All right. Now, like this half of the room has seen the mason jars with the clay. You want to identify which one's which, the blue and the white. What it's doing, if it's encapsulating or inhibiting it. No. There's a prize for whoever gets it right. Yep. What's the prize? No, clay guard. So the blue one is the inhibitor. As you can see, it deteriorates the clay, doesn't let it swell up. And then the white one is the encapsulator. It's still the same. I mean, it just absorbed a little bit, but it keeps the clay, because we use bentonite chips. So that's what's in there. So, and then the third one's water. And you can see how swelled, I mean, it does that downhole. You get a stuck pipe, have a bunch of issues. And remember, once clay swells, you can't unswell clay. So it's already... Yeah. Here, should we get this one passed around? Check it out. What do you think? Okay, gotcha. Okay. So whenever we break this apart, we're going to release the pressure. You don't want it open, blow up on you, mud everywhere. Yeah, thank you. Let's see if I like the thick layer. What do you think? So here's your filter cake. As you can see, thin, smooth. You want it tight. The thicker doesn't mean better. Where's the little ruler? And here we measure it with the ruler. You want it 1/32 of an inch. And I'll leave this up here so you guys could, I'd pass it around, but it's a little messy, so we'll put it up here so you guys could check it out here in a second. What else do we have? I think that's it. Any questions on the testing? Yeah, we'll leave it here so you come up, and I'm going to pass it over to David now.
Okay, we have made it to the recap and review portion of the presentation today. Everyone's still got a chance to pass around our demonstrations and get a look at things. Just to summarize again what you're looking at, there are 3 demonstrations going around. This one over here is, notice that's all clear water. None of that is a full-blown mud. So none of those have bentonite in them, the primary additive of mud. And none of them have multiple additives. It's strictly a viscosifier in water. 2 viscosifiers and 1 just water to demonstrate the difference. And as Jose mentioned, it's about the rate at which they fall. Gravity and water win the day 100% of the time, but what we can do is slow them down. When we slow them down enough, we get that window of time to operate our job and get away without problems. The second thing going around was the 2 types of mud and fresh water in 3 jars. I don't spot them at the moment. There they are. Okay, so they've made their way around. Again, the importance there is that sand and water love each other. Once that water sees sand, the 2 commingle and interact almost immediately, and that is very disruptive to a hole if we're drilling it. Bentonite will do a good job of sealing, and it forms what we call a semi-permeable barrier there, which is what is the actual purpose of that filter cake. But if we add the pack to that, and that's going around, oh, it's not, sorry, is this the pack, or is it around?
No, I already passed it around.
Pack's going around as well to show, there's a jar with just pack in it that shows what pack does when it meets water. And we say there's 2 ways to fight water and when it reacts with your soil. You can inhibit it, which is what the blue jar shows. I'll touch on that in a second. But also you can tie it up. It's like handcuffing the water so it doesn't go and wreak havoc on your soil. We tie it up with pack, and the pack in that jar, I don't know where it is right now. You can see the water, you just added it a moment ago, and now it's a solid. So the pack has completely tied up the free water, and it does that without a visual demonstration of that on your pits, but it does that in reality when we add that to our mud. Now, I'm going to start to touch on a few questions I've had in the break period that we had, and just make sure that I've got everyone covered before we leave here, because that sand came up as a problem that is encountered often, and it's a costly one, it's a time-consuming one, and it's a losing battle, and that's extremely frustrating when we're trying to do something and get it done. So here we had an example. I didn't get the details of where, but there's an extremely unstable sand that is drilled through before we get to the production zone, and that sand, after passing through it, continues to unload in the hole, so that during a shutdown period, if the bit is removed, we can go back in and we tag up 100 feet short, potentially 200 feet short or so. So that sand has totally unloaded into the hole while we shut down for a short period. Those sorts of problems, mud guys like ourselves will typically throw mud at it, but there is a limit, and we all have to be honest about our business. There are limits to every tool's reach, and if you use a tool beyond its limit, bad things happen. It can be a safety thing, or it can be a waste of time and money, or it can, in the worst case, get someone hurt. But where I'm going with that is that when we add bentonite, that's the best sealer for a sand. If anyone's got a pond that they've ever had too much water getting away from it, or a leak in that pond, we seal it with bentonite, right? It's known to seal water. It reacts rapidly it swells rapidly, and it seals off. It forms a semi to mostly impermeable barrier for that water. That's why we use it as a grout at the end of the day. So that bentonite is our primary weapon against a reactive sand, also reactive clays. But with the sand that's unloading in the hole, we're going to absolutely say you need more pack, because we need that extra impermeability to that cake. As we can see, it's demonstrating there. It is working. It's undeniable that it's visually working there, but it may just not be strong enough. That sand may be unstable enough, and it keeps pouring in your hole. And at the end of the day, mud's not the answer. You got to put casing behind it. Put it behind casing. Sorry. That's the truth, the reality of our business. We need to know when to say when, and not just throw money, bad money after good. So my first advice in that one situation, specific to this gentleman's job, was to double the concentrations of mud additives one time and see if we can hold back the sand. And if that does not work, then abandon the mud as your solution, as your tool against fighting that sand, and case it off, which is timely and costly, but at least you're not wasting time on wondering what to do about it and using mud when mud's not the answer. We do have, on the topic of sand, we do have other things that aren't demonstrated here today that are for cleaning, suspending, encapsulating, and lubricating. Because this sand also tears down your equipment, has other unwanted effects besides what's doing down in the well. But for this particular instance, where the sand is coming in at such a rate where we can't hold it back enough to carry on with the operation, casing is the answer. So I'll be the first to admit mud's not always the way to go. Another thing that came up in discussion was contaminants. So these tests here are the primary way that we can identify what the contaminant is, which tells us how to treat it. So a contaminant is going to come across in a way that someone raises a flag. My density's too high, or maybe you haven't even tested the fluid, it's just the mud looks too thick. Or I see pump pressures increasing and I don't know why. Or the flow line looks like gumpy goo and clogs of who knows what, but it's not mud anymore. These sorts of contaminants hit us by surprise. And the way to identify them is with using a certain amount of testing equipment. pH being probably your best, which tells you if you've got a high pH situation, you probably have a cement, or if it's cement, you'd probably know about it, or an anhydrite/gypsum, calcium sulfate. If that's the case, we need to fight that with pH as our number one tool for the battle. So if we can identify what the cause of the problem is, we can properly identify how to fight it. And that, at the end of the day, will save you money on fixing the problem, or at least mitigating it. Because once it starts, we can't completely undo things, but we can prevent them and slow them down from going forward, right? The other way we would see that, if you have someone running this on site, or we've been called out to come look at it, the filtrate would be excessive and the cake would be fluffy. That would also be something we'd see with a solids contamination. The solids contamination would also be identified by a higher density. The pH would remain most likely the same, depending on the solids that are incorporated. But the filter cake would be thicker, fluffier, and less effective. So higher filtrate, higher filter cake, more sticky wellbore is the consequence of that. Potentially stuck pipe, or at least drag when pulling out, tripping. We fix that with dilution. We fix it with fresh mud, or we fix it with better solids control handling equipment that you might, if you have that at your operation. So if we identify these things correctly, again, we fix them. Do I have any other contaminant questions before I move on? I think I touched on what was mentioned to me in the break. Any other questions on that? Sure, acid? Yeah, absolutely. Yeah. These pH strips should go down to the lower acidic level of the scale and show you when you've got an acid problem. And absolutely, we'd fight it with a pH adjuster of soda ash, most likely. There are other ways to adjust pH. There's a combination of sodium carbonate, sodium bicarbonate, which can give you a little buffer. A buffer means that there's some excess in the system that's there. As pH elevates, things become insoluble. They come out of solution. For example, soda ash becomes insoluble above roughly 10.5 pH. At that point, you'll have small particles of soda ash in your mud. You won't see it if it's mud because it won't be a clear fluid, but it will be in there and ready to react when that pH drops below that solubility level. Then that's the buffer effect that we call it, of buffering pH. A carbonate-bicarbonate combination does that even better. It allows more of the pH adjuster to stay in the fluid, so that when it comes out, it easily jumps in and jumps back to solid to soluble form. So it's a quick adjustment in pH. That pH question also came up about our tanks, steel that it might encounter, and how to limit corrosion. Absolutely, pH is adjusted to prevent corrosion. And yeah, 9.5 to 10 is more friendly for steel and reactive metal. Again, with the soda ash, it does have a buffering limit, so you can't really over-treat with it. And what I'm saying is when it's needed, it will come into solution and be used. But you can treat up to about a 10.5 to 11, and after that point, you won't see it go to all 14 of alkalinity because it'll come out of solution. Once it's not in solution, it doesn't affect the pH. So there's a sort of a built-in safety level to using it. So it's a very effective way to keep you safe and keep you out of trouble. And that's all the questions I had, everybody. Let's open forum this for a moment. We've got a few minutes before I let you loose to Grand Ballroom A. And all of this equipment is here. Anyone curious about how to run it properly, even if you just want to look over your mud engineer's shoulder the next time to make sure they're not doing it wrong or not doing it incompletely, for whatever purpose you might have, come take a look. We're going to keep everyone safe. We'll demonstrate with just water. Jose wore safety glasses. With just water, we should be okay. For anyone to come up and feel free to get their hands on the equipment. And if anyone wants to talk to us, Jose and I both have our cards up here. We're happy to take your questions from when you go back and see these things happen and come up, and take it on the fly and go from there. So hopefully it's been of help for you today and you enjoyed the show. Thank you for your attention. Any questions? Come on up. Thank you.
Well, I want to thank you for your presentation. Hopefully, everybody's learned something. Okay, we'll take a little break. Unless there's questions. Anybody got any questions?
Both? Yeah, absolutely. Not everything we can liquefy. There's two ways to do it. We can suspend it in an oil or an emulsion of oil and water, or we put it in water. And you have the trade-off there of it goes into solution quickly and easily. The trade-off is that it's diluted. When it's dry, it's neat. It's 100% active. Once it's in a liquid form, it has a little dilution effect. Even if it's oil as the diluter, only half the jug is polymer and the other half is liquid. So sometimes you want that oil. Not a bad thing, oftentimes, but it does have that trade-off. So they're priced differently, and they last shelf life different too. Yeah, no. We have.
I'm glad you brought that up.
We have absolute field guides. In fact, there's an app. We're not here to promote our company in particular. This is an educational class, but not promoting or not pushing anything. But we have an app. Go to either Google App Store or Apple App Store and look for M-I SWACO, and you'll see our app. That app has field guides of every soil you might encounter, clay, sand, cobble, types of drilling, mining, water well, HDD, and it has formulations. If you're in clay, here's a field guide, gallons, or everything's in different units. You can even switch from imperial to metric and so forth. So MISWACO app is a handy one. If not, if you're old-fashioned like myself, we have it in paper form. We can pass them out. Jose has these individually, or we can email them to you anytime, that sort of thing. So yeah, we have go-to guides for this sort of stuff that you don't want to over-treat with polymers. You're throwing money away, and it's unfortunate to see. So yes. Go ahead. Yeah, NSF thinner. That's a tough one, because the quick answer is no. The easy answer is that the best thinner in water-based mud is water. Truth be told, and it's the cheapest as well. If you've got a thickness problem of your mud, and you've probably over-treated with something, or it's dehydrated, and you can tell dehydrated mud like this. All you need is a mud cup. And you take a sample from your flow line or even your active pit, and you set it on a desk for about 10 minutes. If after 10 minutes there's a layer of pudding on top, your mud's dehydrated. Or you've got too much bentonite. The bentonite sucks up the water. So the two... Yeah, clay does that, yeah. So, sure. Yeah, and they exist. The challenge with thinners is to get them past NSF because they tend to have surfactants like hand soap, and those things kill microbes. That's why every hand soap is antibacterial, and NSF doesn't like that. They do and they don't, but those things, the different surfactants that are used raise red flags with NSF. So it's tough to get one by. That's the easiest answer for that. They do exist. They're tough to get by. And if you can, then with water. Yeah. Another question I had in the break was about salt-saturated muds. I'm sorry I didn't have a slide to touch on that today or get into it in more depth, but if we drill through a large section of salt/anhydrite, we can flip the mud into that system. Or, in other words, if you can't beat them, join them. So if you drill through enough salt, then just add more salt to the mud. It will give you density, but it won't give you the unwanted effects of messing with your bentonite if you have flipped it fully to a salt mud first. And you'll add less bentonite after that, probably none. It depends on how it's encountered. If we plan for it, we won't add bentonite, but we can saturate. When you saturate a salt in a water, what that does is it means that if I add any more salt to that water, it will be a crystal. It won't go into solution. So at that point, the salt does me no harm. So I can drill through it, and it will come out as a solid. So the salt is removed from the well, and it stays stable. It doesn't wash out. It doesn't cause flocculation. It doesn't give you all the trouble that salt can do. So you just incorporate it into the system. Salt can be most often sodium. Sometimes potassium is added. Potassium also has a very good inhibition effect for clays if those are anywhere in your upper or lower hole sections. So if you have the ability to add sodium chloride, adding a bit of potassium, which is compatible to monovalent salts, will blend and mix together, whereas divalent and monovalent, like a sodium and calcium, one's going to compete and win and force the other out as a crystal. But with potassium, sodium, we can use both. And tailor that fluid for your particular area. If it's a gypsum or anhydrite lens or section that you're going to drill through, we can use a gyp mud. It's called lime gyp. And what we do is we elevate the pH very high so that gypsum and anhydrite comes out as a solid material. It's unloaded from the hole, and we move on past it. The other effect of elevating your pH is that you don't wash it out. You don't have it constantly being incorporated into your mud unwantingly. So Those things are available to us. If we know about them, it helps to plan and be ready for them. Again, I hope I've answered everyone's questions today. And come up, please feel free to get your hands on this stuff, and we'll walk you through any details you might have in your mind still.
Okay, thank you.
Thank you.